Everybody say hi, Maddie. Hi, Maddie.
Hi, Maddie.
This is section 2.6. We are on the last section of the chapter. This is a little bit more pleasant than the P over Q method. But there's really four main things that we will talk about in this section. And they are, well, kind of six main things that we will talk about. Two of them we already kind of have gone over. So one of them is domain. Two is the zeros of a function. So we've kind of already talked about those. But specific to rational functions, things that we're going to be looking at further than domain and zeros is number one, any vertical asymptotes that they have. Number two, any horizontal asymptotes that they have. Number three, any holes in the graph that might take place. Or number four, any slant asymptotes. A-S-Y-M-P-T-O-T-E-S. T-O-T-E-S, okay? All right, and we'll kind of write some like notes back up here at the top as we go through VAs and HAs and holes and slant asymptotes, just so you have like kind of a cheat sheet at the top to remember how to find each one, okay? Yeah, you just did this. Okay, yours is at the bottom of your trig paper, the little cheat sheet that you had, okay? First of all, rational functions are like fraction-y functions where you have x's in the top and in the bottom. Actually, you don't have to even have x's in the top. You could only have x's in the bottom. So you have an exponent in the bottom, okay? It's going to be different than like, yeah, it's just going to be a rational function. These are going to be like the boomerang guys, 1 over x, okay? What? Oh, 3 and 4. Holes and slant asymptotes.
Okay, got it.
Yep. Okay? Rational functions look like 1 over x. So looking at 1 over x, okay, we know from the domain that x can't be 0, right? Because we don't want to ever divide by 0, so x can't be 0 and 1 over x, okay? So what they've done here is they've looked at a table and they're plugging in numbers that are really, really, really close to 0. Since we can't plug 0 in exactly, looking at this first table, they're starting at -1, and then they're doing -1/2, and then they're doing -0.1, and -0.01, and -0.001. And what we notice with the y coordinates is they start out like -1, -2, -10. That's not too bad. But then the closer I get to 0, they start going down, 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 down. And that's going to reflect like this left half of the graph, okay? The closer I get to these x coordinate values of 0, the more down, 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 down he goes, okay? Now, if we look at it coming from this way, okay, going towards 0 this direction, we're starting with 1, then we're going to 1/2, then we're going to 0.1, then 0.01, and 0.001, and we're getting close to 0. And what we notice is that the coordinates go on the y values go from 1 to 2, and then from 2 to 10, which isn't bad, and then they go from 10 to 100, and 100 to 1,000. And so we're seeing numbers that as we get closer and closer and closer to this way, they're going up and up and up and up and up. And that's going to be where your vertical asymptote exists, okay? So for vertical asymptotes, one thing that I notice is that the vertical asymptotes are kind of similar to domain, okay? Where your domain like poops out, basically, he's pooping out at x equals 0, that's because your VA is at x equals 0. So like, I'll just write that down. X is not equal to 0. That means that you have a VA at x equals 0, okay? So those two, domain and VAs, go hand in hand, okay? And how do you find those two guys? Like looking at a function. Where does the domain come from, and where does the VA come from? The, what part?
Bottom.
The bottom. The denominator, I can't spell. Denominator equal to 0, okay? So I'm going to put that up here at our cheat sheet at the top. To find a VA, you set the denominator equal to 0. That's how you find a VA, which is kind of similar with domain. You set the bottom equal to 0 to find what he can't be, right? That's vertical asymptotes. That's where they exist. Okay? Horizontal asymptotes. Horizontal asymptotes is going to be on the next page. So here's some examples of vertical and horizontal asymptotes. So they're graphing this function at the very bottom, 2x plus 1 over x plus 1. And this guy, if we set that x plus 1 on the bottom equal to 0, he has a vertical asymptote at -1. Okay, now he also has a horizontal asymptote at 2, and we'll talk about where he's located at. This guy right here if we set this bottom equal to 0, let's check out what happens to that one. So x squared plus 1 equals 0. We would subtract the 1 over, right? X squared equals negative 1. And we're taking the square root of that. So it's really plus minus I, right? Which means the vertical asymptotes are imaginary, which means there is no vertical asymptotes. And you kind of can see that from the graph, that he's not really approaching like high and low. He actually does come to a point. He kind of looks like a polynomial function or whatever, but he actually is coming to a point, so he does not have a vertical asymptote because they are imaginary. Over here, we have a vertical asymptote at 1 because if we set this guy equal to 0, x minus 1 squared, the first thing we would do is take the square root, but the square root of 0 doesn't do anything. It's just 0, and then add the 1 over. So x equals 1 is going to be my vertical asymptote, okay? And he also has a horizontal asymptote at y equals 0, so we will get to that. Okay, good? All right, I know you've heard these rules before because we did them in trig, and Mallory, you just got done doing them in trig. So here's the rules for Haas. Are you ready to go to the back? Go to the next page. The rules for Haas. I'm going to write them off to the side over here. You have to look at n and m for your rational function. So n is going to be the degree of the numerator, and m is the degree of the denominator. I don't know why they call them n and m instead of n and d, but denominator. So degree of the numerator, degree of the denominator. Degree meaning power, like the highest exponent, okay? And there are 3 scenarios that could happen. If your n value is less than your m value, your horizontal asymptote will be located at y equals 0. I'm going to skip down to part B. If your n value is greater than your m value, your horizontal asymptote will be at, well, it won't be at anywhere because there will be none. Okay, so no horizontal asymptote versus y equals 0. If your n is exactly equal to your m, your horizontal asymptote will be the leading coefficient of the top over the leading coefficient of the bottom. If you need to see an example of that would be like, let's say I have 2x squared minus 3x over 3x squared plus 4, okay? My n is the highest power of the top, which is 2. The m is the highest power of the bottom, which is 2. So I look at the leading coefficients. So that would be, my ha would be at y equals 2/3, which would be a horizontal line at 2/3. And that's where my horizontal asymptote would be. Make sense? Okay. So should we go put that at the very top of the first page so you can find it pretty easy? Yeah? We'll go put those rules back up here. So, oh, I'm making you dizzy here maybe. Okay, at the top of this page for Haas, I'm going to go over here and I'm going to say my rules are here. If n is less than m, the ha is y equals 0. That's number 1. Number 2, number 3. 3 says if n is greater than m, the ha is none. And number 2, if n is equal to m, the ha, I don't know why I made my m so weird. M, the ha is y equals LC over LC. Okay, so there's my little cheater rule. So I'm putting everything at the top of the first page. Va set denominator equal to 0. Ha, those are the 3 rules. That's what tells you where the horizontal ones are located. Good? Okay, let's go do some examples. Going back. Making you dizzy, sorry. Here we go. Find all horizontal and vertical asymptotes of this guy. Holy cow.
No.
No. No. Okay, let's do horizontal ones first. Let's do the ha's first. So,
What's it about that it only has to be one away?
That's slants. Just wait. We'll get to that. Okay. All right, so n, what's the degree of the numerator?
4.
Numerator.
1.
1. He's to the first power. M is 4. He's the bottom. Okay. So in this case, my n is less than m. So what's the ha going to be? Y equals 0. He'll have a horizontal line. Okay. And then for Vaz, for the vertical asymptotes.
Leading coefficient over leading.
No.
Vertical.
For the vertical asymptotes?
I thought we went on to the next one.
No. For vertical asymptotes.
Equal to
You set the bottom equal to 0. Okay, so x to the 4th plus 2x squared. This is kind of like finding the domain. We don't want it equal to 0. To find the vase, we set it equal to 0. How do I do that? X to the 4th plus 2x squared plus 1.
You don't.
That is quite odd. What? Break it down. Can you break it down if it's x to the 4th power?
Yeah, x squared and x squared.
If you have x to the 4th, x squared a number, right? It's kind of like a trinomial, and it's whatever. Okay, so I can break it down. What can you multiply to get 1 but add to get 2?
1.
1 and 1, right? So this would be x squared plus 1 and x squared plus 1, right? Okay? And if I set each one of those equal to 0, it's the same thing, right? Okay, you'll subtract the 1, so x squared equals -1, which is going to give me, if I take the square root, x equals plus minus I, which means
None.
no vase. Right? Because if I set each one of those equal to 0, I get imaginary numbers. I get 4 imaginary numbers for the vase. Impossible. Not going to work. No vase. Okay? Next one.
Leading coefficient.
Next one for the Haas.
2/1.
Haas, my n is to the 2nd power. My m is also to the 2nd power. And so I do y equals for my ha. The leading coefficient, what's the leading coefficient at the bottom?
1.
1. So it's 2/1. So y equals 2 is my horizontal asymptote. Okay, just so that we're clear, so you know like what's happening here. If I have this graph, right, my horizontal asymptote's going to be at 2, and this is going to be my dotted line. So he's going to like not touch that line, just so that we're clear like what that looks like. All right. Now this one, when we do the vase, okay, so for vase stuff, we set the bottom equal to 0, so x squared minus 1 equals 0. X squared would be +1, and we would take the square root. So where's my va?
Plus minus 1.
Plus minus 1. I have 2 of them. Well, I don't know what I just did there. Plus minus 1. So I have a va at -1, and I have a va at +1. Okay? Now, what does he look like if he has 2 vas?
He's in between. There's a little volcano in between.
Yeah, so he's going to look one of 2 ways. Either he's going to look like this. He's going to have one of these guys, and then like a thing in the middle. He's going to have like a parabole thing in the middle. He's going to look like that. Or the reverse. Maybe he looks like this instead. Right? Maybe he looks like the green one instead. Or sometimes when that happens, let me go back and do my colors here. I've got this one's at 2, then I've got 1 and -1. Sometimes what happens is you have one here and one here, and you have one like here. Okay, so he might look like any one of those 3 options. Okay, you see what I just drew? It was kind of gross. Yeah, kind of weird. Now the right one is kind of weird because your horizontal asymptote does go through that middle one, right? Okay, now a horizontal asymptote doesn't mean that he can't touch your graph, right? Horizontal asymptote doesn't mean that he can't touch your graph. It just means like on the end parts of your graph, like your graphs are going to like taper toward that line, right? So like here it's getting really, really close to that line. Here it's getting really close to that line, okay? So it doesn't mean that a horizontal asymptote can't go through your graph, right? Because it can. Good, happy with that? It's whatever. Okay. All right, have we talked about slants and holes yet? Nope, we haven't yet. Okay, sketch the graph of that thing. Okay, let's talk about holes really fast. My pretty colors? I haven't yet. I know. Let's talk about a va versus a hole for just a second. Okay, so down here in the corner, let's talk about a va versus a hole. Okay? All right, I'm going to give you 2 examples, and I'm going to change them just slightly. Let's say I have x over x squared, let's say plus 6x plus 8. And then over here, I have x plus 2 over x squared plus 6x plus 8. Okay, so I just changed it ever so slightly. I'm just putting the plus 2 on the top, on the second one. Okay, va versus a hole. All right, let's break these 2 down. I'm making up these examples. They didn't come anyway. Okay.
Or 4 and 6. Or 4 and 2.
4 and 2. So, Va, we're trying to break the bottom down. So let's do this guy. Nope, I gotta use my fancy colors. Break the bottom down. She said 4 and 2. So x plus 4 and x plus 2. So in this case, if I set each one of those equal to 0, I would have a Va at -4, and I would have a Va at -2. I would have 2 Vas there, right? No, if they cross out, that one is the whole. Yes, yes. Okay, so there's how that works out. Happy with that? I have 2 Vas. These are both Vas. Okay, 2 Vas.
Just a line.
Okay.
X equals.
No, don't worry about it being like it's not a line. What are you talking about? Yeah, but that stuff's on the bottom, not on the top. So it's not a linear function. It's 1 over x plus 4, right? So it's not a linear function yet. If that stuff was remaining on the top, then it would be linear. Right? 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 Okay, don't listen to her. All right. X plus 2, x plus 4. However we break it down, that bottom still breaks down like that. But, so I am tempted to say that there's a Va at x equals -2 and x equals -4. I'm tempted to say that there are Vas located at those two places, except the x plus 2's canceled out. So this x equals -2 is actually a whole instead of a Va. Now what about x minus 4?
That's a Va.
He's still a Va, right? But the whole is the place where he cancels at the top and the bottom, right? That's where he reduces. So I have a whole, like a little place where my graph like poops out just at that one spot and then it continues on. But I do have one other Va, right? Makes sense? Just that one little difference. So whenever you have Vas, just check to make sure he's not going to cancel out to the top because Vas look like holes in disguise, right? Okay, good? Or vice versa. All right, happy with that? Can I skip this example right here, sketch the graph of that and go down to the bottom where we're doing slant asymptotes, okay? Last thing, oh, wait. Let's add to our list at the top, okay? A hole, what should we add to our list for holes?
If cancels with top.
Where, numerator and denominator cancel. That's where a hole exists. A lot of times people put it as a vertical asymptote, but it's not. It's actually a hole instead. So check that to be sure. Okay, last thing is a slant asymptote. Last thing is a slant asymptote. Let's go to the third page. And a slant asymptote, they call it an oblique asymptote. That's another name for it. Whatever, I will always call it a slant asymptote. And here, a slant asymptote only exists when 2 things happen. A slant asymptote exists when you have no Ha. If you have a Ha, you can't have a slant. If you don't have a Ha, then you might have a slant, okay? So, no Ha, when does no Ha exist?
The numerator is bigger than
When the numerator is bigger than the denominator, when the top is bigger, right? Okay? But just because it doesn't have a Ha doesn't mean it's always going to have a slant, okay? A slant only exists when n equals 1 larger than m. It has to be 1 larger. So like your top has an exponent of 3 and your bottom has an exponent of 2. If your top has an exponent of 3 and your bottom has an exponent of 1, it's not going to have a slant. And it's not going to have a Ha. It's not going to have either of those. The top has to be exactly 1 degree larger than the bottom. Okay? Here's how you find a slant. You use long division. Okay, so they went ahead and did this. They divided out these 2 things, okay? And if we look at this, our n is 2 and our m is 1, right? This is to the first power, okay? Which means we don't have a Ha, and since he's 1 larger, we do have a slant, okay? And this is what they got when they divided it. They went ahead and did this for us. They divided it and they got this, okay? Here's how you find the slant. This is what they got when they did long division, right? They took this thing and divided by this thing, right? They use long division. You toss the remainder. You don't look at the remainder. And your slant asymptote is going to be y equals this thing right here. Y equals x minus 2, okay? When you graph y equals x minus 2, you go down to -2, and you go up 1 over 1, up 1 over 1. Woo. Just like that. Okay?
Lovely.
And that's what your slant asymptote will look like. Oh heavens. Well, you guys aren't going to be here on Monday. Maybe on Tuesday we'll finish the notes. Do you want me to give you your homework assignment?
I thought on Tuesday
Yeah.
we were doing turkey
Okay.
trivia.
Well, why would we?
What do you mean?
we would
Well,
always-
we'll do the notes and then we'll do some turkey trivia.
Well, like,
Okay?
I'm like,
Bye, Maddie.
no,